Hey everybody, Lars here. Forgive the noise in the back. I have the France-Portugal game on. It's 65th minute and still nobody has scored. I think that's the longest a Euro Championship has ever gone scoreless. But anyway, if I yell goal and I get up, you'll know exactly why. But even though the game is on, I wanted to real quick jump on. This is going to be a quick video, hopefully no more than 10, 15 minutes, where I look at and I show you some stuff about recursion, because that's the second part of the Unit 4 slides. I want you to be comfortable with it. People act like it's super strange and super esoteric, and it's not. It's actually easy to understand when you see some examples and somebody explains it properly. So I'm going to jump right in. First thing I would advise you to do is just go read the Wikipedia page, because recursion comes into play with a lot of other things besides just computer science. It comes into play with language. Language is recursively generated. It comes into play with mathematics, obviously. Recursion is actually an interesting topic, and as it's simply put in the beginning of this page, it just refers to something that when it is defined, it refers to itself in its own definition, which is kind of odd at first. And when we see it in computer science, it's usually when we have a function that refers to or calls itself in the middle of the function, which is a little weird at first, but when you see it in action, you'll see that it's not so bad. I'm going to code one up real quick so that we can see. I set this file up, recur.py, and as usual, I'm going to stick this up in your resources when we're done. Quite simply, I'm just going to create one called mySum, and I will explain it to you after we code it, so don't think you have to know what's going on. If n is equal to 1, return 1, else return n plus mySum n minus 1. Okay. Now, that is a function that will return the sum of whatever the limit is, n, let's say it's 5, of 5 down to 0 added together. So 5 plus 4 plus 3 plus 2 plus 1. Okay? I'm going to call it main. I'm going to say a equals my sum of, we'll do 5 because we just spoke about it. And then I'm going to print a. All right? Let's see if it works first. And we get 15, which I believe is correct. Okay? 5 plus 4 is 9. 9 plus 3 is 12. 12 plus 2 is 14. And add the cherry on top with the 1, and you have 15. So that works. All right? So when we look at this code and we trace through it, let's trace through a slightly smaller example and get 6. Let's see what's going on when we do this. I say a equals, first I have a function definition, but that's just read into memory and not run. Then I have a comment that gets overlooked. Then a equals my sum of 3. So I come up to the function, my sum 3. N is equal to 3. If n, which is 3, is equal to 1, it's not. Else I return 3 plus, and then I call the function again. Okay? Only I don't call it with 3, I call it with 2. I reduce it by 1 and call it with 2. So this is return 3 plus my sum of 2. All right? Now, this is where I think people usually go wrong when we think about recursive functions. When you're tracing through this code in your mind, now you've gotten to this point, you're saying my sum of 2, and people jump right back up here and start doing things again and going over variables that in their mind they think are in these places, and it messes people up. What I try to tell people, and what you're going to see in a minute because we go through another example where I do it, is don't think of it as going into the same workspace or same area. Think of it as a copy of it. Think of it as there being another copy of this function off to the side that we can use. You know what? That's actually what's happening. That's what's happening when your computer and your compiler deals with recursion. It just goes and gets another copy. There's nothing, you don't keep digging down in the same thing as it would seem, going down a rabbit hole or like an Escher painting or something like that. That's not what's going on here. We're just grabbing another copy of it, and you'll see that in a minute. So then my sum of 2. So what do? My sum of 2, is it equal to 1? No. So return 2 plus my sum of 1. So my sum of 1, is it 1? Yes. Return 1. Then I return to the previous function call. So I now have returned 2 plus 1. So I return 3. Where do I return it? The previous function call. The previous function call was 3. Return 3 plus 3. So now I'm returning n. I'm returning n here to this call, because this was the original call. And the answer is 6, and that's what we get out here. Okay? Now, this is the thing. You're building a stack of things, and then when you get to 1, you come up the stack and do the operation. That's the important part right there, the plus sign. Okay? Now, you can change that. Let's say we'll do 1, 4, 5. And we get 15, okay? What if I took this and I made it multiplication? Okay? Now when I run it, I get 120 because it's factorial now. Okay? And just that simply, I'll call it my fact. Just that quick, I've turned this into a factorial. Okay? Save. Boom. $720. This is the important part. That's the operation that's going to get repeated over and over again. And at the end of the day, that's what recursion is all about. Seeing operations where you know you want to do the same operation, but you want to keep doing it on a smaller subset of the list. So if you have a list of 7 things and you want to add them all, well then grab the first one, call the function again. Then it'll grab the first one, call the function until you get down to nothing, and then you'll perform the action as all of those functions report back to each other. Okay? Read the slides. There's that good diagram in the slide with all the parentheses that show how it comes out, and then it comes back in and gets you the answer. Okay? So classically in computer science, when you get taught recursion, you get shown either this, factorial, or I do the sum thing. You also get shown Fibonacci numbers, 1 plus 1 plus 2 plus 3 plus 5 plus 8. All up there, that's easy to generate recursively. But my complaint when I was a young student is that we get shown all these things that we've never seen in any other way before. So the first time I was introduced to generating factorial numbers was with recursion. I'd never seen it done with iteration before. And same thing with Fibonacci. So my point in this part of the game is I want to show you a recursive definition of something you know already that you're used to seeing, so you can see how recursion handles it a little bit differently. And what I usually do for that, as you know if you've read the slides, and I hope you have, is I do multiplication. Very simply, I write a recursive definition that handles multiplication. So when down here, when I call A equals my mult 3, 3, I want to return the product of 3 and 3, which is 9. So if I have this and I run it, you'll see I get 9. And if I made this 4, I would get 12, and so on. We're going to keep it at 3, though. Okay? So I want you to see this, and I'm going to trace through the code. But I'm going to trace through the code in a different way and kind of show you what I'm talking about when I mean go and grab another copy. We are going to look at the code this way. So I'm up here, and if I go back to my code and I look, I say A equals my mult 3 of 3. So I'm calling this function with 3 for num and 3 for times. All right, something's going on. I don't think it was a goal. All right. So when I come in here, what do I have? I have num is equal to 3. I got to draw this. And times is equal to 3. Okay? So if times is equal to 1, is it? No, it's equal to 3. So else return num. What's num? 3. Right? Plus my mult num, which is still 3, times minus 1. Times is 3. So I'm going to call this with a 2. Okay? And when I call this, where do I go? I drop down here to my new copy. So when I do it here, what is num? Num is 3. What is times? Times is 2. Okay? Is times equal to 1? No, it's equal to 2. So, return num. What's num? 3. And my mult num. What's num? 3. And times minus 1. Times is 2, so times minus 1 is 1. Okay? Now, where do I go? I go to my next copy. I'm going to another copy of the function. And here, num is 3, and times is 1, just like I called it. Is times equal to 1? Bingo. Yes, it is. So I return num. So when I get here, I return a 3, because that's what num is. So where do I return that 3? I return it here, because it's the answer to this call right here. So this right here is all equal to 3. So now I'm ready to do this return. Num plus 3 is what? It's 6. So I'm going to return a 6. Where do I return the 6? Right up here. Because this is what the call was for that. So I return the 6 up here. So now I return num 3 plus 6. What is that? 9. Okay? And where do I return this? I return it to the original call. A equals 9, print A, so that when I print the answer, I get my 9, and I'll run it again. Okay? That's what's going on. It looks a little confusing and convoluted here, but if you think about it, and you can freeze this particular screen and sit and stare at it, this is what's going on with recursion. Okay? You're pulling back a number and then going and doing it again. Pulling back a number and doing it again until you're down to 1, and then you come up the stack and you do the returns until you finally get the answer or the number you want. Okay? Recursion is something in programming that you will get used to, and soon you will be able to look at problems, be it addition, multiplication, Fibonacci, factorial, and say, oh, that lends itself to recursion. You might be saying, you know what, I've been multiplying the old way since I was in 3rd grade, and it's been working out for me, so why the hell do I need to do something with recursion? This seems a bit overkill and a bit silly. And what you're going to realize later is that this is how we teach it. Later, you're going to use it in interesting and clever ways, because when we get further on down the pike, you're going to learn about things called binary trees. And at the end of the day, a binary tree is a collection of other binary trees. So if you can write functions and methods that are recursive to work on your data when we set it up as a binary tree or some other data structures that we use in computer science, you're going to find it's incredibly efficient. And it makes perfect sense, and recursion lends itself to a lot of things we do in computer science down the road. Okay? So it's not a complete waste, and it's interesting. You know, it's interesting as a thought puzzle. Not necessarily like learning Latin or anything like that, but it's interesting to look at a problem and say, oh, okay, I can solve that recursively. Look, this is what I'm going to do. I'm going to take my thing that has to be solved, and I know it's a repeated operation, be it subtraction, multiplication, whatever I want to do. I'm going to extract the first number and call the function again. Extract another number, call the function again until I get to the bottom. Then I'm going to do my operation up the stack. Okay? So you'll get to the point where you can recognize where things look recursive to you. And again, and I say it all the time, no goal. Okay, still 0, 0. What's going on here is that I want you to be exposed to it. I want you to see it. When programmers talk about recursion as a Python programmer, I want you to know what's going on. If you want to look things up and play around with recursive answers to things, there are a lot of things Zell does in the book. I know Zell does something with anagrams, and he does a lot of text-based stuff, which is interesting. So I want you to be aware of it, and as you'll see, I'll probably release the assignment number 1 tonight or tomorrow. I just want you to get this video before I give you the recursion assignment, and since that's the first one, I wanted to do this video right now and get it out of the way, even though the soccer game's going on. But I think I got away with it because I still think there's no score. All right? So this is recursion. Take a look at these examples. I will put the multiplication example and I will put the factorial example up in your Unit 4 resources so you have it, okay? I'm not going to kill you with announcements because you already know all this stuff, and I've been sending you email every day. This coming Wednesday, the 13th, the midterm project is due. Last night, I put up all the information for the final project, so now you know that your project proposal is due July 22nd, but you got time to worry about that later. Read, engage with the Unit 4 resources. I want everyone to do well in Unit 4. Slowly but surely over the course of the week, Hans and I will examine all of the Unit 3 things. When we meet in person the next time, we will be going over the Harshed function assignment. So don't send me a bunch of emails saying, I want to see this, I want to see that, We will do that. We will be going over that homework assignment when we meet in person next time. And we'll actually also be reviewing recursion. That's usually what I do in the 3rd class. But this is different because it's summertime. We're only going to have 3 classes. So you're going to be missing out on the 4th class, which I don't think was great shakes anyway. I usually did a lab so that people could work on their final projects. All right? All right. Then I'm getting out of here. I have to go take a handful of ibuprofen and a handful of Tylenol and a handful of aspirin because I have to take this fat old body and play basketball with it tonight. So I need to prepare the temple. All right, you guys be good. All right, and I will be hitting you with announcements all week, so you have no worries. You'll be hearing from me. All right, take care, and I'll talk to you later. Bye-bye.